Right, yeah, so my name's Daniel. I work for Land Digital. I'm technical director. I look after the techie stuff, basically. This was meant to be a practical guide to event sourcing. I wanted to give you a little bit more insight into how the code works and that kind of thing. But we've had a busy couple of weeks and I've had to rein it back a little bit. So this is just a high-level overview. Time at the end for you to ask questions, but if you've got anything you want to ask me while we're going through, just pop your hand up and I'll try and get to you. So, with that said, what is event sourcing? Is anyone familiar with what event sourcing is? Come across it before? Show of hands? Yeah, a few years. Anyone worked with it in practice, put it into production? No. Oh, one. Cool. Grand. You can help out then. Smashing. For the benefit of everyone then, so event sourcing is an architecture. It's an event-driven architecture that is CQRS, so command query read segregation. No. Yeah. That's basically what it's an architecture. Event sourcing is basically where application state is a sequence of unique and immutable events that get stored in an event log. It's an append-only event log, and the event log is the single source of truth. That basically means that state isn't stored anywhere else in the application, just in the event log. So there's no database, no users table, nothing like that. It's just one big event log with everything in. You reconstruct state by basically iterating through all the events and reducing them into a single object, and that's basically how it works. You can sort of think of it as Git for your application state. That's basically how it works. I appreciate that's quite a lot of nonsense. So what does that actually mean? Well, application state is a queue of events. So you think of what a queue is, the difference between a queue and a stack. Queue, first in, first processed. That's basically how it works. So the oldest event gets processed first. Events are not snapshots of state. So you wouldn't have I guess a user record that you would just continuously log an event of. You would log user created, and that would have all the information about user created. And then you might have another event that says user email address updated, and that would just be the email address. It's not a snapshot of the entire row, I guess is how you would traditionally think of it. You can't mutate or delete events. They become a permanent fixture in the system. So basically, if you make a mistake, if you've, I don't know, given an account £10 million, you can't stop that. You have to go in and correct it manually, which is you put another record in that corrects the amount in. You don't go and change the previous event. And that basically means that we've got an audit trail, which is pretty useful in a lot of applications. And it forces a CQRS approach as well. So reading state is intrinsically different to writing state. So if we try and take a look at an example, because again, lots of words probably not making a lot of sense. Before we dive in, we'll sort of explain what our domain is, what the example's domain is going to be. So we're going to model an account because it's easy to visualize. I assume everyone's got a bank account unless you're off grid. Maybe. We'll keep it simple. An account's got an ID and it's got a balance, and we'll be able to create an account, deposit funds and withdraw funds. So our services interface might look a little bit like that. So we'll look at a traditional implementation. So this is hopefully an approach that everyone's familiar with. You've got one model for reading and one model for writing. One model more often than not is one row in the database. That's fairly typical for an active record system. Other ORMs might join across tables, but it tends to be one row. That's what you're looking at. So yeah, this example shows one row in the database. So you can see that we're reading state out of the database, and the key point here is that when we make changes to the state, we're actually writing back to the database and we're overwriting that row. We're changing what's there. And we're working in memory as well until we're ready to commit. So you can imagine a busy account that might have lots of reads and writes happening all at once. We could deposit a load of money at the same time that we're withdrawing money. We might overwrite if the withdraw happens at exactly this, fractions of a second after the deposit. We might overwrite the deposit and the customer loses their money. You can get around that with locking in developer land, so like where you have to actually implement the fix, and you could even go and do it in the table as well. But those kinds of things, they're not inherent to the architecture. They can be bypassed. You can cause yourselves all sorts of problems. Those fail-safes tend to be quite easy to implement badly. And overwriting previous state isn't just the problem, really. You've lost a lot of context as well. So if the client comes to you and says, or a customer comes to you and says, why have I got £10 in my account? You can make a reasonably informed decision. Either you withdrew money to get down to £10, or you deposited money to get up to £10. You can't really be sure how it got to that point. You could maybe log it as a side effect. So when you withdraw money or deposit money, you could log somewhere that this happened, but that's still not really ideal. If you imagine your application's been live for 6 months, and then someone comes along and says, I'd like to see some kind of account line items system, well, you've lost 6 months of data. That's gone, doesn't exist anymore. So you've lost that data, and context is pretty valuable. It's not just valuable to developers, it's actually pretty intrinsically valuable to most businesses. It's data that you can mine. It's also difficult to peer back in time as well, which is actually quite useful for debugging, as well as general data analysis. It's useful for debugging. Case in point, the customer comes and asks, why have I got £10 in my account? If you can go back and literally say, well, this is why it happened, it's much easier to confidently say that with an event source system. And I appreciate that many of the problems I've just been through there, they can resolve them in a variety of different means. Event sourcing is not CQRS, it's not event-driven, it just happens to be a paradigm. There are others out there as well. But the most important thing with event sourcing is that we don't update state, we store events that are generated from some action. So if we refactored that into something that looked a little bit more like events, the service is now decoupled from writing state, it's generating events. The state isn't stored anywhere. It's calculated by layering all of the events on top of each other. And when viewed together, you inherently have more context. So you can see here that we withdrew money before we deposited money. You couldn't see that in the previous system, aside from the fact, you could because I'd put it on screen, but you wouldn't know that from just looking at the database. And this is, it's a trivial, oops, that's not, what's happened there? There we go. It's fairly trivial, but you can see that we created the account before we withdrew funds. Now that's pretty trivial, but in the real world, it's actually quite difficult to reason about certain things. You can make assumptions about them, but in the example of, did I withdraw or did I deposit money, you often can't. So being able to actually see what happened is pretty useful. Some things that you can sort of observe from this, well, maybe, I don't know if we've got enough contrast in the projector. Events generally are past tense. So you would say if you generate an event from creating a user, you would say user created. If you've generated an event from withdrawing funds, funds withdrew. Past tense, it's just easier to read. And you, as I sort of alluded to earlier, you only capture things relevant to the event as well. You don't try and capture everything about, in this case, an account. You only capture what changed and the relevant information around that. So why is this a good thing? Well, hopefully you've sort of cottoned onto the thing I've been trying to hammer home there, which is it's auditable. And it's not just an audit log. As I said earlier, you can build an audit log that is a side effect of change. So when you write something to the database, you could hook into an event that gets fired and write to another table and say this is what happened. But the problem with that is if you do it as a side effect of change, I could go in, if I got access to your database, I could go in and rewrite that audit log. I mean, you wouldn't know, unless you went and looked through the actual database commits, you wouldn't know that I'd done that. You can't do that with an event source system because the event log is the state. If you go back in time and pick a random funds being deposited and you change that number, the system will change, it will update. And what will probably happen is it'll probably crash, but in any case, you'll know that something's gone wrong and someone's tampered with it. I mean, you shouldn't be touching the event store anyway, but if you happen to, that's what would happen. And that's basically because state is actually a side effect of the audit log. That's how it works. Other advantages, I mean, it's pretty easy to reason about. You can follow along. As I said, the events are a general naming convention is past tense, so you can read through the actual events in your store and figure out what's going on. With a pen and paper, you can basically follow an account through the system. We do this regularly. It's easy to think about conceptually as well. This is probably more domain-driven design, but it still applies here because it tends to be how you build an event source system. But it's easier to think about in domain language, I guess, and that makes it much easier for other stakeholders to get involved in designing and building the project. It's actually pretty big, to be honest. I mean, we deployed a pretty big event sourced system, and the kind of questions we were getting from clients weren't, what does this event mean? It was, where has this event come from? And that might be quite subtle, but it's quite powerful. They already understood what the event was. They wanted to know where it came from, which is pretty big, to be honest. And another advantage of it really is it helps when you start building really big distributed systems where you've got multiple domains. You might be thinking microservices. This sort of stuff is much easier. You can quite quickly identify what the domain is, what service you need to be looking at. So it's quite easy to reason about. So I guess if we talked about why you would do event sourcing, we should talk about why you wouldn't do event sourcing. The big one, honestly, is if you don't need an audit log, don't bother. We'll get onto it later, but this comes with its own crosses to carry, I guess, its own burdens. So yeah, how does event sourcing work? As I mentioned, this is just going to be a high-level overview. I wanted to take you through code, but I unfortunately didn't have the time. There's lots of materials to read and watch out there on this sort of stuff. Martin Fowler's got some really good videos. He's wrote some really good articles on it. Spate, you've got an ebook as well, pretty reasonably priced as well. That's where we learned most of what we learned. Pretty good, gives you the basics of what you need to do and how to work it. And there's some really good frameworks out there as well. So Spate, again, have a Laravel framework. You can get off the ground with event sourcing really, really quickly with that. It's got its downfalls when you start to hit sort of big scales, but it gets you off the ground quickly. You've also got Prof, which is a set of loosely coupled components to build an event-driven system with, an event source system. You can build just a generic CQRS system with it as well. It's really nicely decoupled. And then you've got probably the one most people have heard of in the PHP community is event source. So that's a framework of interfaces, traits, and abstracts, and it's less of a framework in terms of here's an opinionated thing you can go and build with. It's more a case of here's all the tools you need to go and build an event source system. Now off you go. Very, very good. I'll try and share some resources at the end. I've got a slide with the resources on, and I imagine we'll be sharing the slides. Mm-hmm. Yeah, we'll share the slides. So yeah, let's take a look at some of the basics then. So a diagram. This is my best impression to try and show you how an event source system works, I guess. So you issue commands to aggregate routes. Aggregate routes generate events. That nice snake there is your event log, slowly building up, and the events then get propagated out to the rest of the system to be reacted to, processed, whatever. Yeah, these are the sort of the main parts, really. The commands drive the aggregate routes. The aggregate routes collect events together and propagate events out to the rest of the system. The projectors project things into a query layer for us, which we'll get onto in a moment, and reactors, which do something in response to the events. Again, we'll get onto all this in a moment. So let's look at what aggregate routes are first. So that's sort of a loose interface of what an account aggregate route might look like. So you've got something to load it out of the event store to begin with. You've got the account ID and the balance, which are read-only because you can't mutate them. You have to put events into the system to do that. You've got a method to persist them. So if you've made changes to it, you can then persist it back into the event store. And then you've got methods to create, deposit funds, and withdraw funds. Fairly basic, looks like a fairly benign service in most systems, really, and they're not particularly special. But aggregate routes, what we do with them is, if you cast your mind back to the account example we had in a traditional system, then you've got an ID. You tend to have an ID for most things that you have in your system, most objects you have in your system, and it's the same with aggregate routes. All the events that the aggregate route generates for that ID get stamped with that ID as well. So if you want to pull those events out of the system, you use your aggregate route ID, and what it does, it goes and queries the event store for all the events that match that, and then it reduces them all into the aggregate route. I guess you could sort of think as an aggregate root a bit like a data transfer object. I mean, it does a lot more than that, but that's effectively what it is. It's a data model for the things in your system, the state of the things that are in your system, like an account. Aggregate roots do more than that, though. They also are basically where your domain logic lives. It makes sense because an aggregate root is responsible for basically maintaining the data integrity. So it stores the events, it makes sure they go into the event log with the appropriate aggregate versions. So when events go into the event store, you log what aggregate version that event is for, and that basically stops any concurrent writes from overwriting previous state. So if you've got two concurrent tasks accessing the same account, and they both try and write back, one of them will hit the database of the data store first, and that'll capture whatever the next event aggregate root version is. If the one that's a little bit behind then goes and tries to write with the same aggregate version, it'll stop because it's normally a unique key. If it's a relational database, it's a unique key, and it will stop it from writing that. The whole thing will fail. And if you've wrote your application properly, we didn't in some places, it'll roll back whatever it's done. But yeah, probably sounds like a lot of responsibility for one thing to be doing. It's a lot of the complex stuff is abstracted away, really. The aggregate root looks after events for a domain object, so it makes sense that it proxies domain logic as well. In practice, as I said, the recording, the publishing, and the collecting of the events tends to be abstracted away. You don't deal with that stuff. It's normally actually split out of your class and is handled elsewhere. So we'll quickly solidify what events are as well. I'm aware we've talked a lot about them, but events are data transfer objects. There are immutable records in state. Hopefully people are familiar with PHP 8.2, I think this is, with read-only classes and things like that. That's basically what they are. You can't change them. Once they're out in the world, you can't change them. They are sequential in nature. They have a sequential ID. They're typically time-stamped as well, but that depends on your own implementation. Probably something that's worth noting is you can imagine that's account created there. If you start adding additional fields to your system, you have to change your events. If your events are stored in a log somewhere, what you actually have to do is you have to have transformers to map old event shapes onto new event shapes. It's fairly easy to do. It's just something you've got to be aware of with this kind of thing. Again, I sort of alluded to earlier, unless you need an audit log, this sort of system comes with its complexities, its own trials and tribulations. Events are often, probably no surprise, propagated outside of the system as well, and that's fairly typical. You'll have events getting fed into a message queue which other systems can consume. That's particularly the case if you've built a distributed system or a microservice type system. You will be sending them out to a message queue somewhere. What more complex systems can do is they might have another layer on top of the events where events get scrubbed of specific domain data. Like an event view layer, effectively, to sort of mask some of the internal workings. Someone who's late. It's the world's squeakiest store, don't worry about it. Yeah, so events can get propagated outside the system, and sometimes you'll try and mask some of the implementation details in your events before you send them out to the world. Yeah, let's take a look at how we create some events. So we sort of looked at aggregate roots. And the service had methods where we could create an account, withdraw funds, deposit funds, that kind of thing. You typically wouldn't you typically wouldn't work directly against an aggregate root. What you would typically do in a CQRS system especially is dispatch commands. So, just bear with me, yeah. Commands are, again, they're basically just TTOs. So again, you've got read-only classes here. You don't once you build a command, you don't tend to change it after that. It's a command that gets issued, and that's all it is. It gets dispatched to a bus, and the bus then matches it to a handler, and the handler does the actual work. So what the handler would typically do, and it depends on your use case really, but it would retrieve the aggregate root parse the command and then play the command against the aggregate route. So you wouldn't, if you had that in a HTTP controller that receives a request, you wouldn't go and manually pull out the aggregate route and then create an account. You would just build a command and dispatch it to the bus and let the system figure it out. And the aggregate route then creates the events. Why commands are not working directly against it? Well, for a number of reasons, really. It lets you build more, orchestrate more complex actions, I guess. So if you've got a command that, I don't know, charges someone's card, you might have a payment gateway that you need to go and access first before you actually go and issue any events and things like that. So that's what you would do. It's easier to orchestrate multiple services into a command. It's a bit like actions, I guess. And the aggregate route has a defined scope of responsibility as well, so it doesn't make sense to put that kind of external services stuff in the aggregate route. Another thing about commands and CQRS systems is they're typically fire and forget. They tend to be asynchronous. I mean, that is one of the things of a CQRS system. The command gets fired, and then at some point, whatever the read layer is will become consistent with what the command did. That means that you can execute them in parallel. So if you've got a controller that is running, that is firing off multiple commands, or would be typically doing multiple things, if you didn't use commands, asynchronous commands, you'd have to wait synchronously for each one of the aggregate routes to update, and given that it's inserting into probably quite a busy event store, that can take a while, that can snarl you up. But ultimately it helps build distributed systems. If you're building something using event sourcing, you probably are going to end up distributed at some point, and commands help with that. It basically means that, I mean, using our example, our account service wouldn't have to know the ins and outs of how our overdraft service works. It would just need to speak the same language, which is the commands and the events. Yeah, that's commands. As far as event storage and messaging, I'm sure most of you have probably played this through in your head by now and figured that you can end up with quite a lot of events in a system, and you can. Ours has been live for about 18 months and is on about 200 million events now, so it's staggering how quickly it's going. And we've had our fair share of scaling issues so far, but nothing insurmountable anyway. So events can basically be stored anywhere, but realistically you want to put them in a database. Don't put them on a file system, you'll have a terrible time. You can use a relational database, or you can use highly specialized databases like Event Store or Kafka. And then for message queues to communicate across systems and domain boundaries, you can again use Kafka, or you can use things like RabbitMQ. It basically boils down to personal preference. You've just got to balance that against the system's requirements. Postgres can handle really big databases, for example, like Airbnb have, I think, always used Postgres. I think they migrated to AWS Aurora, but that is basically Postgres underneath. It's just managed at massive scale. So, you know, a standard database can do that. Kafka is built for this sort of stuff. I mean, it is basically an event streaming system. That is what it is. But it can be pretty difficult to set up, especially for the uninitiated. And PHP support is, I'd say, community built. It's not really. The guy who built the Kafka client for PHP is now one of the core maintainers of PHP, but it's still not something that's in the core. It's something you have to install yourself. So yeah, I assume a few of you wondered how it scales. So like I said, lots and lots of events are in ours now. I guess the next question would be, if you have to spin through all of the events to get the current state, surely that takes a while, and it does. So there are nice little shortcuts that we can take. One of them is projectors. So the reason that traditional systems haven't really gone anywhere is because almost all questions that you can have about a business and its domain can basically be answered by its current state. Very rarely do you need to go back and look at its previous state. So we can deal with that. We can project our events into a schema that looks like a traditional database. So you've got a account created event, you have something that listens to that event and creates a row in an accounts table. Now you've got a pretty standard looking system. that basically makes it far, far cheaper to read state out of the system, and it's very much in line with traditional database performance. And that's basically the read layer of CQRS. You've now got a separate layer that does just that. It's not only cheaper, it's much easier to interrogate, to be honest with you. If you've got to interrogate the event store for anything in depth, you're gonna have a bad time. We've brought production systems down by trying to query the event store. Not fun. Yeah, but if you put them into a relational database, for example, you can join, you can group, you can order things. If you put them into a NoSQL database, you can do whatever you need to do. You can put them into graph databases, query it that way. It just makes it a little bit easier to interrogate your data. And because we've basically got every event that ever happened, we can replay the projectors if we want. So if, I don't know, in our case, we managed to dump a load of email addresses into our system that was case sensitive, and we put all our email addresses in uppercase, you can replay your projectors and correct your rather serious fuck up without many people noticing. It's really useful though. Like if you want to go and add, if you've got a pivot table that you need to go and build, typically in a traditional system that would be pretty difficult to do if you've already got lots and lots of data. In this, you just play it through a projector. It might take a couple of days depending on how big your data set is, but you've got your pivot table and off you go. The problem with projectors though is you can't really use them when you're writing changes, because CQRS, which is basically what this is, and event-driven systems, there's no guarantee of when events are delivered and when they're going to be processed. It's asynchronous. All you know is that it will eventually be consistent with the head of the event store. So you can't really use these for writing state because they might be out of date. But there's a way we can get around that as well, which is snapshots. So what we basically do, instead of calculating the current state for every single time we want to pull an aggregate root out of the system, we snapshot it. So every 50 events, we generate a new snapshot, something like that. That massively reduces the load, and basically all a snapshot is a record of an aggregate root state at a given point in time. And what we do is we store the last event that was processed on that snapshot, so that the next time we need to go and get the aggregate root, we pull the snapshot out first, we get all the events that have happened since then, and we just play them on top of the snapshot. And hopefully that's only a small handful of events, and it doesn't take very long to do it all. Yeah, as I said, periodically taken. Generally it's every so many events, and it's substantially cheaper than rebuilding state from scratch every time. Again, ask us how we know. We ran into that problem quite quickly, and it's not an easy one to fix. So if you do this, definitely take snapshots into account and design them into your system to begin with. But if you think about an accountant's ledger, this is basically what they do as well. An accountant doesn't have an enormous book that ends up this high off the ground. What they tend to do is they have annual accounts, and they just take the last line from the previous financial year's accounts and just put it into the new financial year's accounts, and then they just start again. It's just easier. And then the final bit of the puzzle for an event-driven system, well, for any event-driven system really, is reacting to events. And they are rather inventively called reactors in event-sourced systems. So yeah, the name implies it, they react to events. And they're basically tools for maintaining domain boundaries. So I sort of hinted to it earlier with the account and overdraft services. Imagine those are two different microservices. If the overdraft service spits out an event that says interest charged on account, well, the account system's going to have to react to that, and it's going to have to take that into account on the account's balance, which is where reactors come in, basically. So it's basically a way of building a truly event-driven system. You start listening to other events coming from other domains and reacting to them. But it's not just keeping state, or not keeping what you would traditionally define as state, I guess, up to date. It's for things like sending an email. Account created, you might send a welcome email, or you might want to send a fine if you've built a particular system that charges people for going through a tunnel. Yeah, projectors, I guess you could think of projectors as specialized reactors. They are, for all intents and purposes. And that's sort of the key components of an event-driven system. So what are some of the challenges? Well, like I said, we've built this. I probably should have said this at the top, but I didn't want to hear everyone boo. We built the time tunnel system in this. Yeah, we got away with it for the most part. There was nothing major. I mean, I say we brought production systems down. We haven't. We've got plenty of failover, but we have had some moments where we've thought we were going to go down. We haven't went down, just degraded service. So yeah, we've got first-hand knowledge of what some of the problems are. So some of the ones that are specific to event sourcing, I mean, the biggest one is the event store itself. Like, you are committed to keeping every event that is ever generated by the system. So I did some quick math earlier in the week, and I think in 10 years' time we'll be on for about 2 billion events, which is a lot. I mean, Postgres can probably take that much. Who knows? We'll find out. But yeah, like it's costly. Like that's basically storage space. It's processing space. It's a lot of maintenance overhead as well. I mean, you can ask the ops team how much maintenance they've had to do on it so far. It's quite a lot. And then another one, I mean, I don't know whether anyone's had this in the back of their head yet, but GDPR, it's an enormous pain in the arse. The events cannot go anywhere. They're in the system. It's not insurmountable, but I haven't touched on it here because it is a topic unto itself, basically. If you want to have a look into it, it's called crypto trashing. And the basis of it is that everything in this, every object in the system, so every account, every user, whatever, everything that gets an account, gets a aggregate root ID, gets its own public-private key pair. You encrypt all of the personally identifiable information with the public key when it goes into the system, and then when you want to delete it from the system, you just forget about the private key, and now you haven't got access to it anymore. And I'm assured that is in compliance with data protection until quantum computers come around, and then, yeah, all bets are off them. So some more specific ones to sort of general event-driven and CQRS complexity. Like, there's a lot of moving parts in this, and event-driven systems can be unpredictable. If you're just sort of sat in your little bubble in your own little domain, making changes, spitting out events, people are subscribing to them. The effects can be cascading. And the big one that people tend not to think about is backwards compatibility. So I sort of hinted to it earlier about having to transform events when you want to add new properties into them. You have to be mindful of that kind of stuff, and you've really got to try and think about stuff ahead of time to try and predict where you're going to end up. And then debugging, I said earlier that it's really helpful for debugging, and it is, but it's a double-edged sword. Event-driven can make it much harder to do because a developer hasn't directly, I guess, dispatched an event. No one's asked for it to happen. It just happened in reaction to something that a user did, and users tend to find ways of breaking systems, and they do. They're very good at it. What's probably worth noting is that I think it's probably exponentially more difficult to keep, I guess, the system state in your head with every degree of separation you get between events. So if you imagine you've got, I don't know, a user-created event, and that dispatches some command, eventually dispatches some command to go and create a customer in Stripe or something like that. If there's a number of events between them, and there often can be, it's really difficult to try and follow them through, because when you go and query the event store for those events, you end up with 50, 60 different events. Not fun to try and get through sometimes. I mean, it does help. You can normally very easily justify what the system's done and say it with a matter of fact, but it can take a while to get there, and it can often make you want to bang your head on a wall quite hard, which I haven't done yet. I think another one really with generally just big systems, I guess, is onboarding, especially with domain-driven systems. I mean, time tunnels, it's about 500,000 lines big now, so when we need to onboard new developers, it takes a while. But it's not just onboarding them. As I said, this is more of an issue with domain-driven design, but if you're doing an event source system, you probably want to follow that. But it's not just the architecture that you've got to learn, you have to actually learn how the customer's domain works. So you have to really learn what on earth does, why would I get fined in this particular scenario? You need to understand that like the back of your hand, otherwise you're not going to be able to work on that particular part of the system. And then probably the last one, I sort of hinted at it earlier with events, where to store your events, is like what tools do you use, what frameworks do you pick up? Is PHP really the best one? It is. Well, perhaps not the best one, but it's more than suitable for what it is. But where you store your data, what sort of message broker you use, things like that, those are questions that can paralyze you, and it's often best just to dive in and figure it out later. Otherwise you will be sat trying to figure out the differences between, well, the various different configurations of Kafka, which isn't fun. It's not fun. So yeah, that is basically the challenges.